let's look at this question. Find all normal 2 by 2 matrices that are real. So I explained that a matrix is normal if it commutes with its adjoint, where this adjoint means you take the trace, you take the transpose, and then you take the complex conjugate. But in this context, the complex conjugate doesn't do anything because we're working with real. I just want to see what 2 by 2 matrices happen to satisfy this. So let's write a generic 2 by 2 matrix as A, B, C, D. That means A transpose bar, where A, B, C, D are all real numbers, okay? So the bar doesn't do anything. Transpose simply means the diagonals are fixed, but the off diagonals, they switch places. So you have A, D, same thing. And then here comes the B, and this is C. Let's now, this is our A star. Let's now compute A times A star, which is A, B, C, D times A, C, B, D. And that gives you AB times AB, that's A squared plus B squared. AB times CD, so that's AC plus BD. CD times AB, so that's AC plus BD. And CD times CD plus C squared plus B squared. AC plus B. All right. What about A star times A? Then it's AC, BD, AB, CD. This time it's AC times AC, so that's A squared plus C squared. ACBD, so that's AB plus CD. BD times AC, so it's AB plus CD. BD times BD, so it's B squared plus D squared. And since we're asking these two matrices to be equal, if you compare them, you see that A squared plus B squared should equal to A squared plus C squared, which in turn says B squared equal to C squared if you subtract A squared both sides. And that in turn says that B should either be plus or minus C. Now let's look at this other one. Oh, that's the same thing. B squared, D squared, same. C squared and B squared has to be the same. They will be same if B and C are just either equal or negatives of each other. So now the other condition is these two. So you have AC plus BD equals to AB plus CD. And there are two cases. Case one, if B is equal to C, see, either B is C or B is negative C. I just want to track those two cases out. If B is equal to C, then AC plus CD, I'm just replacing B by C. Since B is same as C, I'm going to replace B by C. Then the left side becomes this. The right side, again, becomes the same thing. So it's always true. But there's another case, which is that B is equal to negative C. In that case, you have AC minus CD. I'm replacing B by negative C. And negative AC plus CD. So this time, I can move this over here, move that over there, and we get 2AC equals to 2CD. So actually, let's just move everything on the left side, okay? So if I move everything to the left side, I get 2AC minus 2CD equals to 0, which is 2c times a minus d equals 0. So there are two cases. It's either c is 0, but then if c is 0, then b is 0, then they're both 0, so you end up with case 1. So this actually brings you back to case 1. Is that okay? If c is 0, then b is also forced to be 0, then they're both 0, so it's case 1. So when b and c are non-zero and they're negatives of each other, what you actually get is that you're forced to say a and d has to be equal. So here's our answer. The answer is that there are two classes. Either you have A, B, B, D. So B and C should be equal, so you get A, B, B, D. And that's the case where it's symmetric, right? This is self-adjoint. Well, self-adjoint means that A star is same as itself, so it's kind of trivial for this case. If you take the, if this is A, then A star is itself. So this condition is almost trivially true. It's just saying that A squared is equal to A squared, so nothing special is going on. Or, in the case when you have B here and then negative B here, then you're forced to say that these two are the same, so it has to be A and A. So this is another case where you have a, so this is another case when you have a real normal matrix. So that actually tells you that there aren't many normal matrices as you think. If you randomly write down a 2 by 2 matrix, in most cases you're not going to find it to be normal. So you might think, well, where does the word normal come from? It doesn't seem that prevalent. Like, usually most matrices are not normal, so what do you mean by normal? Well, the word normal actually comes from the fact that the eigenvectors will be perpendicular. So let's talk about that.